Greetings everyone! Dear Energetics 2020 conference participants, I'm Nenad Petrovic, a teaching assistant at the Faculty of Electronic Engineering, University of Niš, Serbia, from the Department of Computer Science. In what follows, I will present you the paper that we wrote together with my colleagues Vasil Roblek from Faculty of Organization Studies in Nova Mesta, Slovenia, and Professor Valentina Nekovic from my university. Our paper is entitled Mobile Applications and Services for Next Generation Energy Management in Smart Cities. It is certain that efficient energy management is of utmost importance in smart cities. On the other side, data-driven mobile applications play an essential role when it comes to information exchange in urban ecosystems. Therefore, in this paper, we introduce a novel approach to rapid development and dissemination of smart city mobile applications related to energy management. As a proof of concept, two case studies are presented. The first one is energy-efficient smart home consumer device management, while the second is energy-aware computing infrastructure management in fog computing architectures. When it comes to technological background, the two main technologies behind the implemented applications are AppSheet and AR.js. AppSheet is an online development platform which enables highly automated and intuitive creation of multi-platform mobile applications relying on cloud data sources and Google's infrastructure. As an advantage, it offers development of highly sophisticated mobile applications without almost any coding. Furthermore, it offers a set of advanced machine learning and artificial intelligence features such as optical character recognition, voice commands, and value predictions, which is leveraged in this paper. In what follows, the workflow of AppSheet-driven mobile application development will be described. First, the data sources are specified. In our case, we rely on Google Sheets for that purpose. After that, formulas and predictive models making calculations based on the imported data are defined. Furthermore, the user interface is generated by selecting one of the available options for data visualization, such as table, chart, graph, histogram, and so on. Once the views are created, application behavior in terms of actions and trigger can be specified, making use of high-level declarative language. And finally, user has to download AppSheet client from the corresponding App Store in order to run the previously created application. On the other side, we have AR.js, which is an open source library for JavaScript enabling high-performance augmented reality applications to run in web browser even on dated mobile devices. Moreover, it offers a wide set of features such as loading 3D objects, their animation, marker recognition, and position-based augmented reality. To make the things even simpler, the ideology of this framework is quite straightforward, enabling implementation of complex systems in just few lines of code. Apart from the previously mentioned commercial technologies, this paper also relies on some of my previous works. Data-driven framework for energy-efficient smart cities has the following features. Household consumer device monitoring based on affordable IoT devices such as Raspberry Pis and Android smartphones. Load forecast mechanisms and anomaly detection in electric signals leveraging deep neural networks implemented using TensorFlow in Python programming language. Relay production system using Arduino Uno. And finally, energy trading framework based on blockchain technology leveraging linear optimization. The objective function of the underlying optimization model aims to minimize the overall costs, taking into account the ratio between trading and generation costs, and also it is summed with distribution cost. Furthermore, there is a constraint that all the smart homes participating in energy trade should still be able to satisfy household demands. On the other side, SmarterFog is semantic-enabled, model-driven framework for modeling, simulation, deployment, and adaptivity of services within fog computing infrastructures, taking into account both traditional servers and IoT devices such as Raspberry Pis. It relies on Docker technology for service deployment in form of Docker containers. It also leverages linear optimization mechanism for energy-aware optimal service deployment to the available devices. The objective function aims to maximize the ratio between service performance and energy consumption. Now, we'll take a look at the generalized architecture of the presented case study applications. First, the devices of interest, such as household consumer devices or fog computing servers, are monitored and corresponding data inserted into Google Sheets. After that, the measured data is visualized to the end user within the AppSheet application. The users are able to take corresponding actions depending on particular context, which can additionally trigger some effects, such as turning on or off the devices, deploying services, and so on. Apart from the AppSheet application, the user is also able to make an input using augmented reality user interface based on markers. In most cases, these triggers rely on the previously described frameworks, which are in this case invoked as external services. External frameworks take user-provided parameters from mobile applications as input in order to perform linear optimization with the goal of optimal energy exchange or energy-aware computing infrastructure management. Now, we'll see the first case study application. It relies on data-driven framework for energy-efficient smart cities, as it was mentioned before. There are three main screens within the application. The first screen provides a complete overview of electric devices connected to the grid. For each of them, it is possible to change the state, to turn it on or off, see if there are some anomalies, see the current energy consumption, and see the predictions for energy consumption in next periods. Moreover, on the other side, it is possible to participate in energy trading between smart homes, which are part of blockchain network. In this context, the deal propositions can be offered to other homes whether to buy or sell electric energy. This feature mainly aims the so-called smart grid prosumers that are able to both produce and consume electric energy. In what follows, the augmented reality user interface for consumer device management will be demonstrated. First, user has to point camera to the marker beside the consumer device. After that, a 3D cube appears showing the summary of status information. If we put hand over the marker, then we will be redirected to the corresponding device page in AppSheet application. When it comes to the second case study, it relies on Smartphone for deployment of fog computing services. The first page of the mobile application gives complete list of the available devices. The second screen is a list of services. They can be either running or stopped. And the third screen is actually the mapping between the devices and services, so we can allocate a certain service depending on the current demands and hardware requirements for each task to some particular server. For each of the devices, there is a more detailed view where users can see the list of services running on their device, either turn on or off some of the services or the device itself, see the characteristics and parameters of particular device, a number of connected users, and current electric consumption. In a similar way, we can see the requirements for each of the services or deploy them to a particular device by clicking the deploy button. After that, linear optimization procedure selects the most appropriate device regarding both energy consumption and its location, cloud or edge. After that, finally, the command for Docker is constructed and the container is deployed on the selected device. A similar marker-based augmented reality user interface application was also created for this case study. By pointing mobile device to the marker, the information about current number of users connected and electric consumption prediction is also shown. Finally, it's time to see some evaluation aspects of the proposed approach. For evaluation purposes, the devices with given characteristics on this slide were used. The mobile applications were run successfully on both Android and iOS operating system. The following evaluation aspects were considered. Development speed up time, which actually shows that the proposed approach is much faster than developing cross-platform applications using state-of-the-art frameworks such as Xamarin, Flutter, or similar. Moreover, the delivery of the updated versions of the applications is done in just few seconds compared to traditional approach where user has to install new application from the App Store and wait for a few minutes. When it comes to prediction accuracy, it's just slightly worse than the previous works, as here we use the AppSheet module enabling in just few clicks to train a neural network and perform predictions, while traditionally we need to use TensorFlow and implement a custom neural network, which is a time-consuming task. So we can say that performance is satisfiable. And finally, the service response time is in order of magnitude of 10, but it actually depends on external frameworks as well. To sum up, the proposed approach really has many benefits. Apart from that, it also enables to non-programming experts to create applications that will solve problems from particular domains. Thank you for your attention. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.